Export to cloud. All righty. All right, guys. So welcome back. It's Monday. Hope you guys had a good weekend. I know a lot of you were probably working, not just on homework, but your actual jobs. I guess one quick reminder, homework 6 is out. Okay, it's going to be due on Wednesday. We are going to do a homework party Wednesday afternoon, like right after lecture is what I'm going to be planning for. So right after lecture, I'm going to try to get like 2 hours in the student center again, and then you can come. Yeah. Yeah. I might try to just stick around like all of Wednesday afternoon, but I might just not have a room available. But I will, like, if you're around on campus, I'll just try to be on campus and then just, or check my office if it's like after 3 p.m. or some, it's so weird because like you guys can't get in after 3, but yeah, just email me if you're like still around. I'll try to stick around like all afternoon and just kind of be generally available. But I'll do like a little homework party right after, and I'll have Chi join us on Wednesday because I think normally her student hours is 1 to 2 anyway, so she'll be there as well. So yeah, yeah. So just that's a reminder. And then the other thing, we do have a. So you guys open that up. I'm gonna do it a little bit differently today. So actually, what I'm gonna do is I'm gonna try to do it together in class and then take like a vote from the people that are here in person. So we're gonna like read the question. I'm gonna give you guys like, 30 seconds, 20 seconds or something. And then I'm gonna ask, what do you think the answer is? And then we're just gonna take it together from my account. You should also take your own quiz, okay? So you still need to take it. It's still gonna be open till midnight, but I'm gonna try this thing to like try to save time in case, because I've noticed maybe a lot of people don't necessarily understand the answers. So anyway, let's get started. So the first question is actually this. If you have not already and would like to, please sign up for the mock technical interview with Meta Engineers early April. So you can just click this link, okay? When you click this link, it's gonna ask you to log into your Piazza account because we're using Piazza to schedule. And there's still quite a few open slots, okay? So please, if you like, I encourage you, like sign up, like even if you don't have time to prepare, even if you feel like you're not gonna do a good job, it's just a good experience and we're not recording any, like, it's not, like if you do really well, like we'll probably try to figure out who you are and like reach out to you. If you do really, really poorly, we're gonna forget. Like nothing is being recorded. And the engineers that are doing the interview, these are folks that are trained to do interviews. So they're doing regular interviews. And then they will also save 10 minutes at the end of the interview to like give you verbal feedback, like actual, like, by the way, like this is what I thought about your solution. And like, here are the parts where like, I think you did well. And like, here are the parts where you didn't do so well. And I think you could improve, okay? So again, normally you don't get that sort of feedback from interviews, right? But for these, you will be given it to verbally. So you can try to sign up. There's a bunch of open slots. Again, please try to make it if you do take a slot. I don't know, you might be able to cancel a slot. I don't know how it works, but just try to keep it up to date if you can't make it, just to make sure that other people have the opportunity to, okay? So that's that. So yeah, let's vote on this. How many people said, thanks, I signed up? 1, 2, 3, 4, 5, 6. Okay, 6. Awesome, I'm interested, but I don't feel ready, prepared. 1, 2, 3, 4, 5, 6, 7, 8. Okay, no thanks, I'm not interested. Any no thanks? No thanks, okay, so we'll go with this one. All right, so the next question, consider the following graph for the weights. The numbers on the edges are meant to represent the cost of walking along an edge, okay? Suppose you do BFS, starting at node A. Let me zoom out a little bit. Yeah, if you guys could take a look at question 2, I think this should be your question 2, hopefully. I'll give you guys a few seconds to think about it, then I'll poll the class, okay? Yeah, maybe I'll do like a timer. How do I do a timer? Stopwatch. Okay, I'll give you guys 30, let's say 20 seconds to think about this, and then I'll start doing a quick poll. Okay, that's 20 seconds. Let's try to speak out the answer for this one. Who wants to speak? Who wants to propose an answer? Yep, go ahead. A to B to C. Okay, who agrees that A is the correct answer for this question? Raise your hand. 1, 2, 3. Okay. Who has another proposal for an answer? Yes, Serena?
I think it might be just A to C if the BFS isn't considering weights.
Cool. Do you want to, right. Do you want to explain why it is A to C?
Yeah, because we didn't specify that the BFS was taking weights into account, so it would just be directly A to C, which is 1 pound.
Yeah. Yeah, so if you remember, BFS does not handle weights. It does not look at weights. It just looks at edges. So in this case, it will, the shortest path will be the one that has the least number of edges, which will be just A to C. Okay. So we're going to go with that one. Okay. I'll give you guys 10 seconds to read this question. It's very similar to the other one. Does somebody want to give a stab at this one? Yeah, Vincent? Yes, so in this case, we're taking the weight into account. It's ABC. Which algorithm would find this shortest path? What's the name of the algorithm? Yeah. Dijkstra, D-I-J-K. I think he's German or something. I don't know. Yeah, so he's got a weird name. Okay, what? He's Turkish? Not Turkish. Okay. Yeah, so ABC is the shortest one here. All right, so let's take a look at this one. So this should be well, I'll give you guys 10 seconds to read this question. Yeah, the links to the quiz is from the lecture and then also from the course website in the announcements. Oh, the announcements are not up. Okay, I'll fix that later. But if you can get to the lecture notes, that'll have the link to the quiz. Actually, let me see if I can fix that. Well, actually, let's. Who wants to give an answer for this one? I hear Dijkstra. Any other proposals, or does anybody disagree? Okay. Yes, the answer is Dijkstra. Well, we don't want to use BFS because it'll be based on number of edges, right? Not the weights. DFS does not do shortest links, right? It does not do that, right? Cool. All right, so what about this question? Select all the scenarios where we can use Dijkstra to find the shortest path. Can we use Dijkstra to find the shortest path in a graph with negative? Yeah, Jonathan.
I was gonna say the second option. I was gonna say everything but the first because you can't have a negative extra.
Okay, so yeah, that's a good proposal. So let's start with definitely not the first. Does everybody agree with that? Okay, definitely not the first. And then yeah, we only did it with directed graphs when we were talking in lecture, but you can imagine you can very easily do it with undirected graph as well, right? So okay, this is actually a little bit more interesting. So I'm going to give you guys 20 seconds to read this question. This setup we're going to use for the rest of the questions. So take a second just to read it and think about it. I am going to fix the course website while you guys do that. Okay, all right, so while we wait for the website to deploy, let's jump back to this. All right, so first question, what is the minimum possible length of the shortest path from node A to node B? Any suggestions? Yeah, David? Okay, so somebody mentioned maybe it's 5 because it's a value stored in DB. Anyone disagree with that, or we all think it's that one? Yes, maybe. You also think it's that? Okay, we've got 2, 3, 4 people. Okay, we've got quite a few people think it's that one. Okay. Any other proposals, or are we gonna go with that one? We're gonna go with that one. Okay. You guys are wrong, so think about that. But we're gonna go with that one. Okay. All right. Let's go to the next question. What is the maximum possible length of the shortest path from A to B? Yeah. Yeah. Yes, that is a great question because that will help you answer these, right? So if we remember from lecture, these numbers are the numbers that we are updating as we run Dijkstra. So at the very beginning, the DA we set to 0 and everything else we set to infinity, right? Because they represent an they're an overestimate. They're like a worst case scenario of what the shortest path could be, right? So at the very beginning, we don't know anything. So we say, well, they might be infinity. And as we run the algorithm, if you guys remember, the numbers get only smaller because we always take the minimum of either the existing number or some alternative path, right? So as we're running it, they're getting smaller and smaller. And then once a node has been marked as sure, so once we finish picking it up from the ground, so once we're done processing it, whatever number is here is the shortest path. Okay, that's the claim for Dijkstra. So what we know here is that we were in the middle of running Dijkstra and our computer crashed. We were working on node C. So we just picked up node C. So that's the one that we know that one's been picked up off the ground. Okay. And we know that its overestimate for the shortest path is 4. Okay. So the reason the answer here is actually 2. Minimum possible from A to B. Yeah, so the reason the answer here is 2 is because you don't know that you have finished node B. It could still get smaller, right? But you do know that yeah, so it could get smaller than 5. You do know you finished node C, or you like picked it up at least, because that's the one you're currently processing. So any paths that were shorter than 4 have already been completed. That's the other thing to notice, right? If from A to C, there was a string of length 4, then anything else that was closer already got picked up. So that actually means that DE here equal to 2, that is the shortest path. So for E, you do already know the shortest path, okay? For C, you just picked it up. So you also kind of know the shortest path, okay? But for all of the other ones, the numbers are an overestimate on what the shortest path could be. Okay. Does that is like exactly the question you want to ask? Yeah.
Okay, so then how is 2 the smallest number if we haven't quite picked this?
Right. So we don't know. So the minimum possible length of the shortest path from A to B. It's actually 4. Yeah, you're right. Yeah, it's 4. I was wrong. Yes. This is 4. Wow, I'm sorry, I tripped myself up. You're right. Good point. Yeah, it is 4 because we know C is the smallest, not yet finished. So anything that was shorter, we would have already picked up. Yeah. So the minimum for this one's actually 4. Does everybody like that? Yeah, good. Sorry, you caught me. Good one. Okay, this is going into the details of Dijkstra. If you understood that, you are golden. Okay. If you did not, I encourage you to try to think through it a little bit more. Right. So given that information, what is the answer to this one? What is the maximum possible length? Yeah, Jonathan.
Because you haven't figured out the rest of the path yet, because you stopped at C.
Not.
You haven't picked up the other ones yet, so.
Yeah, you haven't picked up the other ones, but remember, we are updating our guesses. So the paths start as infinite, and we always update them every time we pick something up, right? So yeah, Vincent. Yes. So this one, the answer is 5 because so remember, DB started as infinite, but now it's 5, which means at some point we found some path that was at most like that was 5 lengths to be. So we don't know if that's the shortest path, but we found a path that was 5, right? Yeah.
I have a question. So like if it crashed at C, you're saying it's picked up. So would that already have been completed in order for it to go to C?
You don't know how the graph is connected. So you just know that you have these nodes, but you don't know what connects to what. Yeah. And you don't know their lengths either. So that's why this question is hard, I would say. Like if I told you the graph, then you could just run Dijkstra and then you would know the lengths for each one, right? Okay, so last 2 questions. Let's minimum possible length of the shortest path from node A to node E. So we just talked about E. Yeah, it's 2. And actually, you can say something further. 2 is the shortest path. You know 2 is done, right? Because in order to process C, for which your estimate is 4, you had to pick up everything that was already shorter. So you're actually already done with anything that has a shorter estimate. Okay, so that's actually 2 here and 2 for the next question. And if we run Dijkstra's algorithm on a graph of the US street, roads, highways, etc., starting from Greensboro Science Center, which of the following locations will be the first node to be picked up? Yeah, Jonathan?
I was thinking A because, like you said, each time you run it, you could basically find a new first node each time that you run it as the shortest path, but the Bandito burrito is already in Greensboro, so you know that it's already there in regards to versus Times Square and the Hollywood side. Bandito burrito is already in Greensboro, so all the other 2 choices, you know that one will be before the other.
Right, right. And I will say you always we always start from the Greensboro Science Center. So we always start from the same place. And then this is a map of the entire US. We have every single location you can imagine into this graph. So if we always start from the Greensboro Science Center, do you want to change your answer at all? Or do you want to commit to one of the 2? I think you mentioned both, but I don't know which one you want to commit to. Yeah, Sloan? No? Just between these 2, you want to just flip a coin and guess? Somebody want to? Yeah, so the Bandito burrito is going to be the first one we picked up always. So Dijkstra is a deterministic algorithm. Every time you run it, it will pick up the nodes in the same order. And the way it picks them up is it picks up the ones that are closest to you, right? So essentially this question, no matter how big the graph is, out of these options, it'll always pick up Bandito burrito first because it will get to it first because it's closest. Okay, cool. All right, let's go ahead and move on to lecture. You guys feel free to submit that quiz and give it a shot. Okay, so like I said, reminders, mock interviews are, you guys should sign up for that. Homework 6 is due on Wednesday. And also the last day to withdraw from a course without a grade evaluation, I was asked to remind you guys, is March 28th. I don't know if that matters a lot to you guys, but All right, so today we're actually going to cover a new algorithm called Bellman Ford. We're going to finish Dijkstra up first, but Bellman Ford is actually, I think, an easier algorithm than Dijkstra's, but it's slower. Okay. Bellman Ford is also one of the first algorithms we're going to see that uses something called dynamic programming. So this is a new technique that we're going to be introduced to over the next week as to how to solve problems efficiently. Okay, so remember the techniques you guys have basically learned so far are sorting and divide and conquer. And you learned a couple of graph algorithms, right? To like explore graphs, but that's it. We are going to start introducing a new technique called dynamic programming. Okay, so that's today's lecture. Bellman Ford is an example of an algorithm that uses dynamic programming. Okay, cool. So I guess just to remind you guys, a weighted directed graph, this is what it looks like, right? Connects nodes, you have edges, you have weights. The weights represent the cost. The cost of a path is the sum of the weights along the path. The shortest path from S to T is a path from S to T with the smallest cost. Okay. And then the single source shortest path problem, which is what BFS solves, what Dijkstra solves, is to find the shortest path from S to all of the nodes in the graph. Okay. So you won't get the shortest path from B to T. Okay, Dijkstra is not like if you start Dijkstra at S, it will not tell you what is the shortest path from A to V. Okay, what it will tell you is it will give you an answer for the shortest path from S to U, S to V, S to B, S to T, and S to A. Okay. Again, so look, for example, this is a path from S to T that has cost 22 because edge 1, edge 21. This is a shorter path that has more edges, but has shorter path because it has lower cost of 3, 5, and 2. So the total cost is 10. So it's actually shorter. Okay. So that's just a reminder. I think last time we didn't get around to actually talking about how fast Dijkstra's algorithm is because we want to analyze the running time. So here is the pseudocode for Dijkstra's algorithm that we discussed about. These 3 steps. So this step, set all vertices to not sure. What is the running time of that? That step, doing that process. Think about like, what's the running time? Got this? Sorry. O of V, O of how many vertices you have, because you go through each one and you set them to not sure somewhere, right? So this is going to be O of n. So we say n is the number of vertices, m is the number of edges. Okay. So what about this? dv equals infinity for all v in v. What's the running time of that one step? How long would that take to do if you were coding it up, right? What would you have to do to code that up, right? Looks like a for loop, maybe, over each node. Okay, so again, O of n, all right? How long does this step take? ds equals 0. So my start node, I'm going to set its estimate to 0. Constant time. Okay, we're just setting a value equal. All right, then we talked about this. We have this while loop. Okay, so while there are not sure nodes. Okay, so while I still have nodes that I have not marked as sure. Okay, we're going to ignore this part right now. And we're going to notice that on each iteration of the while loop, we mark it as sure. Okay. And nowhere else do we take a sure node and mark it as not sure. Okay, so ignoring what's inside the while loop, how many times does this while loop run? O of n, because you pick up a node, you mark it as sure, and nodes never become unsure again. So you will at most pick up each node once, right? So now the question, so this, you can ignore this part. So now what you want to know is you want to talk about what is the running time of the stuff inside the while loop. Okay, so you have n here, n here. You know this while loop runs n times. If this was constant, if this work was constant time, what would be the running time of the algorithm overall? If this was constant, which it's not, but if it was constant. I heard O of n, it's O of n, yeah, because you have O of n plus n, right? N iterations, one per vertex. So now the question you want to answer is actually how long does each iteration take? So you can forget everything else, and now you can just focus on looking at the stuff inside the while loop and see, okay, how long does that take? Okay, and that's what we're going to do. And it actually depends on how you implement it. Okay, so first we're going to talk about the running time without actually giving answers. We're going to talk about it abstractly, and then we're going to say, I can implement it in different ways. Okay, so this is just the inner loop. Again, we forgot everything else that we just talked about. We wrote it down, but now we're forgetting about it. So what we do, we need something. We need a data structure, right? Because what we're going to do is first we pick the not sure node with the smallest estimate, right? So somehow you need to be able to look at all your nodes and pick the smallest one, right? Somehow, right? And there's many ways to do that, right? Then we look at each of the neighbors and we update their estimate, right? We calculate the min. So calculating this min is going to be, what's the running time of calculating the minimum of two numbers? O of 1, it's going to be constant, right? So this part, you know, it's constant. But this part where I'm saying update, okay, depends on how you implement it. That's all I'll say. And then you're going to mark U as sure, which is basically constant. You don't have to worry about it. Okay. So we need a data structure that's going to store all of our vertices that we haven't processed yet. That's going to keep track of our estimates, DV, and that will let us find the minimum value easily. You know, that's kind of the goal, because that's what you're doing. Those are the three things you're doing in this loop, right? So we need a data structure that has find min, like a find min function, right, to give us the minimum, that can remove the minimum value when we want it. And that can also, we call it update key. It can update the value associated with a particular node. Okay, so that's the data structure we're looking for. This is like an abstract data structure. It's not a specific one. Okay, this is just like, these are the APIs that this data structure needs to have in order for us to use it in this algorithm. Does that make sense? Okay, so given this information, what's the running time of this algorithm? So you don't know how long each of these take, but what would be the running time of the inner loop, for example? So it's kind of like a weird question I'm asking you guys, because I want you to count essentially how many times you call each of these functions, because you don't know how long they take to run, but you want to count like how many times you would run them. So how many times do you call find min, do you think? How many times do you need to know the minimum node?
Every time you need to compare to the last value.
Right. So on each iteration of the loop, we find min one time, right? When we're looking for the minimum one. So on each iteration, we call it once, right? How many times do we remove min? How many times do we mark a node as sure, basically? Do we get rid of it? One time per iteration, right? How many times do we update key? How many times do we update the value associated with the node? One's a little trickier. It's kind of hard to think about, but yeah.
Does it depend on how many neighbors that you have?
Yeah. So you can look here. It's basically like how many neighbors does you have, right? That's the number of times within each loop that we do it. But let's take a step back and think about the whole problem. So overall, after we'd run the loop n times, if we look at everyone's neighbors once for each node, right? We look at its neighbors. How many times do I call update key? Where n is the number of nodes and m is the number of edges. Somebody said what? Oh, m plus n. It's actually m. But m plus n is also correct, because like big O, the m is bigger, so the n doesn't matter. But yes, it's m. So update key gets called once per edge. That's another way to think about it, right? So again, a lot of times when understanding the running time, it is helpful to look at like each line, right? So for sometimes you look at each line and you say, I know this takes constant time. right? But sometimes it's more helpful to kind of like take a step back and say, well, what is the algorithm doing, right? Each edge is actually only considered once, right? Because we consider each node once and we look at its neighbors, which means it's looking at those edges. Those edges, well, each edge is considered at most twice, I think. Well, actually once. So we look at those edges and then we never again consider them, right? Only the outgoing edges. And then we never look at that node again once we're done. We look at another node, okay? So the running time, if you put that all together, this is the more important one. It's n times how long does it take me to find the min, plus how many times do I remove it? Because you guys said we do that n times, right? Each of those. Plus m times how many times does it take me to how long does it take me to update a key? Okay. That's the general running time of Dijkstra. Okay. Now, let's talk about specifics, right? So how would you implement this data structure? So the easiest way to implement this that you guys maybe have thought about already is you can use an array, right? So an array is a data structure. To find the minimum of an array, so you're going to keep, all your estimated nodes that are not sure, you're going to keep them in an array. It's not going to be sorted, nothing fancy. You're just going to keep them in an array. To find the minimum is going to take you O of n time, right? Because you have to iterate over the array. That makes sense? To remove the minimum, to get rid of some element in the array, it's going to take you O of n time because you don't know that it's going to be the last or the first. It could be any element, and you're going to have to like shift all the elements back one when you remove it. Okay. To update a key, though, it's going to be constant time because to update the value of an array, you can just look up the index and you can update it. Right. So with this data structure, what's the running time of Dijkstra's in terms of n and m? So we said it's n times find min plus remove min, right? So that's n times n plus n. So that's going to be n squared plus m times update key. So update key is constant, so it's just m, right? So the running time in this case is O of n squared plus O of n, right? Is this a good running time? What do you guys think? Right. So that's O of n squared. It's actually not that good. We're actually going to cover a worse algorithm today. So like it's good compared to that, but it's not that good. Okay. Let's say now we say like, well, I didn't like using an array, but I do know other data structures. For example, a red-black tree. So in a red-black tree, finding the minimum is going to take me log n time, right? Because the tree height is n, and it's a balanced search tree, right? So to find the minimum, I just keep going left, 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 left until I get to the bottom, right? To remove the minimum also takes me log n time because I remove the node and then I have to rebalance the tree, which takes log n. To update a key also takes me log n time because I don't remove the value, I change like its key, like what it's associated with, and then I have to make sure it's in the right place. So I have to rebalance the tree, right? So all of these take log n time with this data structure. Same question, what's the running time of Dijkstra? If it's the plus m times log n, right? So the running time is this. Okay, is this better than the previous running time? Or is it worse? Okay, I hear some betters. Does anybody disagree? Does anybody think it depends? It kind of depends. Because remember, m is the number of edges. If I have a graph that has all the possible edges, right, then m is actually going to be n squared, right? M by itself, right? So that will be n squared log n is going to be the running time, right? If I have to basically, in the previous iteration, right, the previous running time, I had n squared plus m, right? In the worst case, I have n squared edges, right? I have a really fat graph that has everything connected. So the running time is going to be O of n squared, no matter what, right? Now, if I have a really fat graph in this running time, my running time is actually going to be n squared log n, which is slower than n squared. But if I have a very skinny graph, so let's say the number of edges is like 3 per node or something, right? So it's a very sparse graph, that's what they're called. Then the running time is going to be n log n, which is actually better. So it depends. If your graph is going to have a lot of edges, you actually want to use the first algorithm. If it's going to have very few edges compared to the number of nodes, you want to use this one. Okay. Do you see, like, so these are the sort of things that you actually would do like when you're working at a job. Because once you get to really difficult questions, usually there is no like single right answer. It's like you need to understand it, and it kind of depends, you know. Like if I'm, you know, if I'm making a graph that is all the roads in the US, that's actually a very sparse graph because, you know, like New York City is not connected to Chicago, right? Like there's a lot, like you're only connected to the stuff close to you, basically, which is, so you have very few edges per node. So you would use this algorithm. But if you are making a graph that is like, you know, who's friends with who inside this classroom or something, maybe that graph's a little bit more dense because people tend to be friends with a lot of other people within the same group or something. So something to consider. Okay. All right. So there is another data structure that is much better, which is actually called a heap. We are not going to cover this data structure. There are many different ways to implement min heaps. We are not going to cover these, but again, I'm just like computer science, everything I teach you, you guys are learning a lot. This is like 2% of everything there is to learn, right? So for heaps, you can look up on Wikipedia and you can see that there's many different ways to implement heaps. And in fact, the one we're going to look at today, the one that turns out to be pretty good for Dijkstra, is called the Fibonacci heap. Okay, it's implemented using a union set data structure, which we are not going to cover in this class, but you can click the Wikipedia links and you can go down that rabbit hole to understand it. There's many other ones, but the things we care about are, for this heap, finding the minimum is constant, decreasing a key is constant, and deleting the minimum is log n. Okay, so again, we're not covering it. I'm not explaining why this is the case. A lot of times you just know this data structure exists. So if we use a Fibonacci heap, what's the running time of Dijkstra if I use a Fibonacci heap now? So it's going to be n times find min plus remove min. So it's going to be n log n plus m times update key, which is actually constant. So we actually get an algorithm that has n log n plus m running time. Now, you should be skeptical of this because this data structure seems like too good to be true. These running times are not what we call big O running times. There are other, so again, when I teach you stuff, you're learning like 10% of what there is. There are other ways to analyze algorithms. In this case, they're called amortized running times, which means, what it actually means is it means a lot of your operations are very cheap, constant time, but every now and again, you have to do something really expensive. So every now and again, your computer is going to spend a lot of time finding the minimum. Okay, but after it does that, there will be a lot of operations where it can find the minimum in constant time. Okay, so we're not going to cover amortized analysis, but that is, if you're interested in that, there's a lot of data structures that work that way. And the lecture notes have some more information as well. Okay, so in practice, we'll skip this slide, but basically, Dijkstra using Fibonacci heap is what most people use in practice because it's pretty good all of the time. It doesn't matter what your graph is. Okay. Okay. Dijkstra is also used in practice a lot. So again, if you guys like, these algorithms are actually like implemented in just so many places. So Dijkstra is actually used for the open shortest path first, which is a routing protocol for IP networks. Okay. So if you guys are taking a networking class, talk to your professor and be like, where do you guys use Dijkstra? He might be able to point you to the actual code somewhere on GitHub or wherever. where they implemented Dijkstra to like solve this routing problem. Okay. But again, there are some things that Dijkstra is not very good at. And we covered these a little bit. So one of the drawbacks is that it only works on non-negative edge weights. Okay. If you ever have negative edge weights, it's not good. The other drawback of Dijkstra is that if the weights change, if one of your edges changes weights, right, for whatever reason, you actually have to rerun the whole algorithm in order to find the new shortest path. There's no way to say this edge changed, now update only the paths on that edge or something like that, right? You actually have to rerun Dijkstra from the beginning. So this algorithm we actually talked in practice. The way it works is every computer broadcasts its because when you're routing in a real network, the cost to send messages is going to change, right? It's not constant, it's not fixed. So what actually happens is every computer broadcasts their updates to every neighbor, and then they all run Dijkstra again to try to keep updated as to what's the shortest path. Okay. As an aside, a negative cycle is a cycle whose edge weights sum to be a negative number. This is going to be important later. Shortest paths are not defined when there are negative cycles. And we're going to talk about this in a little bit, so you don't have to worry too much. But you can maybe you can think about like why, if I have a negative cycle, it just doesn't even make sense to talk about shortest paths. Does somebody want to take a stab at why it doesn't even make sense to talk about shortest paths if my graph has a negative cycle? Sure, Serena.
Well, since -10 is like so much larger than like 2 and 1, you can just go in a cycle forever and like continuously get a smaller and smaller number. Right. So the shortest path is like negative infinity, because I'll just be, well, I'll just take this cycle over and over and over and over again, and it'll just keep going down, right? Okay. All right, so let's jump to the Bellman Ford algorithm. So this is an algorithm that is slower than Dijkstra's algorithm, okay? But it can handle negative edge weights, okay? This can be useful when some edges are actively good to take rather than costly, okay? It can also be useful as a building block for other algorithms. And Bellman Ford actually allows for some flexibility where if an edge gets updated, you just need to run it for one iteration and then it updates everyone, okay? So again, Bellman Ford versus Dijkstra. Dijkstra finds the U with the smallest estimate, DU. Then it updates all the neighbors to be the new estimate, either what you estimated before or going to U first and then taking the edge UV, right? Whichever one is smaller, we'll take that one. Bellman Ford is dumber. It doesn't bother with finding the smallest DU, okay? Just updates every node. That's it. That's the difference. So if you know Dijkstra, Bellman Ford just says, I don't want to be smart. I don't want to pick the smallest one because I know that's the one that got picked off the ground. Just update all of them. Okay. Again, this is the pseudocode. So for Bellman Ford, the difference is that instead of pick the not sure node U with the smallest estimate, you say for every node in V, do the update. Okay, that's the difference for Bellman Ford. Now, if you do this, right, the smallest estimate, remember if you think back to the proof about Dijkstra, this relied on the fact that you couldn't get the estimates to become smaller after you had picked up the node. So that's why if you don't have negative edges, you can just pick the smallest estimate up, and then you know there's not going to be an edge later that will make some estimate on the ground be actually smaller than the one you just picked up. Okay, so if you don't have negative edge weights, this works. This always works because it's just saying update it for everything. Okay. So we're going to start with an example again. So going back to our beloved traveling across campus. So same graph as we did with Dijkstra. This time we have no negative edges. Okay. But we're just going to walk through Bellman Ford to see how it works. Okay. So the very first thing we do is we set our estimates to 0 and infinity, right? This is the same as Dijkstra. And then we look at every single node and we do a new updated estimate where we say
the minimum of your previous estimate or the new estimate to U plus the edge weight from U to V. Okay. So who wants to fill these in? We'll do dynamic programming next lecture. Don't worry. This is dynamic programming, but like we'll talk about dynamic programming more abstractly. But who wants to fill this in? What goes here? Yeah, so this stays the same because we're going to do 0. We're going to compare 0, right? So we always look at what's above you. So you take the minimum of what's above you plus for any edges coming into you, you need to find the minimum. I guess actually you can just do it, right? So you can say for every U in V, right? So for each node, for all of my neighbors, so these would be outgoing neighbors, that neighbor is going to be updated to be the minimum of its previous estimate or my current estimate plus the edge, right? So if you start with this node, you would say, well, I have two neighbors, Clock Tower and Aggie Terrace, okay? Both of these, Clock Tower is infinity, Aggie Terrace is infinity. So I'll take the minimum of infinity or 0 plus 1. And then this one, I'll take the minimum of infinity or 0 plus 25, right? Okay. And the difference between this and Dijkstra is Dijkstra does the same thing, but it only does it for Aggie Village because it says there are no negative edges, so I don't have to worry about anything else. What this algorithm does is then it says, okay, do the same thing for Health Center. Okay, so now look at all the neighbors of Health Center, which are Clock Tower and Aggie Suites, right? And then it says, okay, for Clock Tower, what if I first went to Health Center and then I took this edge? So it says, well, what I currently know is it's either infinity. Wow, this is not working. My previous estimate was infinity. My newest estimate is 0 plus 1 going here. And then if I go to Health Center first, I estimate that's going to take me infinity because this one currently has infinity as its answer, plus this edge, which is 1. And you take the minimum of those to update Clock Tower, which again gives you 1 as the answer. But you do that then for Aggie Suites as well. And then you do that same process for every single node on the graph, okay? So the answer you're going to get is 0, 1, and 25, which is actually the same answer Dijkstra gives you. These end up still being as infinity. And I think one thing I want you guys to notice is intuitively, the way this algorithm works is it's considering all possible paths that only have I edges. Okay, so when I equal 1, all of the paths from Aggie Village that are 1 edge long will be updated, okay? Whereas any path that requires more than 1 edge will remain at infinity, okay? And the I increases every time. And why does that work? That's because, well, for this one, this is all paths that have 0 edges, let's say, and then everything else is infinity. This is the paths that have 1 edge. And then what we're going to do is we're going to look at all the edges, basically, and we're going to take the minimum of 1, paths that have 1 edge. And then if I add 1 more edge, what would be the minimum now? If I could use 1 more edge, right? So I encourage you guys to look at this example slide and lecture, like think through it. We only have 1 minute left, so I'm going to go a little faster. But this is what the second one looks like. This is what the third update looks like. And this is what the final update looks like. It does actually return to you the shortest paths, okay? Yes. Again, like we said, an intuitive interpretation of DIDV is that it is equal to the cost of the shortest path from S to V with at most I edges, okay? That's the intuition as to why it slowly builds up to actually find the shortest paths, okay? And also you can tell like the ones that are infinity are the ones that are too long in the sense that like all of these require one path, at least one path, but I'm not looking at one. I'm looking at paths that only have 0 length. Here, I'm looking at paths that only have 1 length. Here, I'm looking at paths that only have 2 lengths. Okay. And let's end it there, I guess. So you guys have now learned another algorithm that does work with negative edge weights. I will be around in my office till 3 p.m. today. So if you want to come say hi, come say hi. And we will cover, so this is a dynamic programming algorithm. We will talk about how it is a dynamic programming algorithm next lecture. Okay. All right, thanks everyone on Zoom. I'm gonna stop sharing, but thanks for coming. See you guys next time. Thank you.